Assalamu alaikum wa rahmatullahi wa barakatuh. Hello everyone. Welcome to lecture 11, Organic Chemistry 2. We will start today on chapter 3, Reactions of Aromatic Compounds. We will talk about electrophilic aromatic substitution reactions. Benzene react with electrophilic reagent E plus Y minus to substitute carbon hydrogen bond with carbon electrophile bond. The first step will be attack of the double bond to the electrophile, forming what we call sigma complex, a rhenium ion. So when we attack, we form positive charge in here, which then delocalize over the cyclic ring, causing stability of this intermediate. In step 2, do we add Y minus to E plus, or we eliminate the hydrogen out and regenerate aromatic system? Of course, loss of proton, regain aromaticity and give substitution product, and we get substitution product. So as we mentioned, the first step is approaching the double bond, the E plus, to form the first transition state. This is the first transition state. Okay? Then formation of sigma complex as an intermediate cation. It is non-aromatic system. That's why the reaction is endothermic. All right? The second step is the removal of hydrogen getting out to form another transition state, which then go very fast to the product substitution. So the first step we call the rate determining step. Rate determining step is the first step. Halogenation of benzene, first example of electrophilic aromatic substitution. Benzene is normally unreactive in the presence of halogens, because halogens are not electrophilic enough to disrupt its aromaticity. Remember the halogen X, single bond X, with 3 lone pairs on each atom of the halogen. So there is a symmetry. So there is no X plus actually in. Scientists use the behavior of Lewis acid-Lewis base character to form a complex, and this complex indeed will have polar X plus. So halogen may be activated by Lewis acid catalysts such as iron halides, ferric halides, or aluminum halides to become more powerful electrophile. Seen here, we have lone pair attack on the iron to form complex. Now in the complex, BR-BR bond is polarized, thereby imparting electrophilic character to bromine atom. So even in this one here is partially positive because it's connected to positively charged Br in the complex. So can donate and two electrons and form a double bond and becomes plus. So with this polar Br plus, the benzene ring will attack Br, and this bond will break to form the sigma complex intermediate. The anion species will then attack on the hydrogen as a base to eliminate the hydrogen, regenerating the aromaticity, the aromatic system, forming bromobenzene. Examining the overall reaction, bromination reaction, using iron bromide, iron 3 bromide, as a catalyst, starting material bond dissociation energy, carbon hydrogen dissociation energy 112, Br 46. Here product carbon Br 81, carbon Br 87.5. So the total change in the enthalpy will be starting material 112 plus 446 minus product 81 plus 87.5. That gives out energy 10.5 kilocalorie per mole. So overall reaction is exothermic reaction. Exothermic reaction. For chlorination reaction, benzene plus chlorine, iron 3 chloride to form chlorobenzene plus HCl. Bond dissociation energy of starting material 112 for CH bond, 58 for CCl bond, 96 for CCl bond, and 103.2 for HCl. Total difference in enthalpy will be minus 29.2, exothermic again, but with higher energy. So we are going from bromine going up to chlorine. The chlorine is much more exothermic reaction. For the fluorination, going up one more, we will find out that bond dissociation, again CH112, fluorine 38, carbon fluorine 126, and hydrogen fluorine 135.8. So the total difference between the starting material and the product is exothermic 111.8 kilocalorie per mole. So as we go up, the reaction is much more exothermic. It's actually fluorination, direct fluorination is exothermic, and reaction of fluorine with benzene is explosive. In iodination reaction, this time we are going below the bromine, going down. For iodination, the bonds involved in here is a CH from benzene, again 112 bond dissociation, iodine 36. For the formation of bond dissociation for the I bond 56, and HI 71.3. So the overall enthalpy change is 11.7 kilocal per mole. So this reaction is endothermic, and Lewis acid failed to create iodine electrophile. So if we react iodine with Lewis acid, that will not create I positive for the benzene to attack. However, stoichiometric amount of an oxidant like nitric sulfuric mixture can be used for the conversion of iodine to I plus. We call this reagent Tronov-Novikov reagent for iodation. So iodination will take place by taking iodine, nitric, sulfuric to give I plus, nitrogen dioxide, and water. So here nitric acid is not a catalyst. Nitric acid is a part of the reagent. And the reaction will go smoothly. Electrophilic addition to form sigma complex with two different resonance structure, followed by elimination of proton to regenerate the aromatic ring benzene and form the iodobenzene. Similar mechanism is seen for cupric copper-2 chloride and hydrogen peroxide with iodine. These reagents creates iodonium ion. Also, we can make the iodination using iodine monochloride with aluminum Lewis acid, aluminium chloride as a catalyst, and we get the iodobenzene and HCl out. This reaction goes smoothly too. Sulfonation of benzene. To synthesize a real sulfonic acids, we use a mixture of sulfuric acid, sulfur trioxide as electrophile. The sulfur trioxide is a powerful electrophile. To understand why, sulfur has its p orbit, its p electron in 3p, while oxygen has its p electron is in 2p. Difference in size makes the interaction or the overlap of the p orbitals not complete. So we say that sulfur trioxide present in the resonance structure, as you can see here, where sulfur has a positive charge and oxygen has a negative charge, and here a single bond. That can be clear in the electron density map. Looking for here, the red means higher electron density and the blue electron deficiency. And it's clear that sulfur, this position, has electron deficiency. So sulfur trioxide is our electrophile. Reaction of benzene with sulfur trioxide on sulfur attack to form sigma complex, which again stabilizes by resonance, and then deprotonation to form the aromatic system once again, and finally proton transfer to form benzene sulfonic acid. Aromatic sulfonation is really a reversible reaction. So if we can get the benzene sulfonic acid with water and catalytic amount of sulfuric acid heated up, we take the reaction back to benzene, and we call this hydrolysis reaction. Sulfonation of substituted benzene is used in many industrial products, among them the detergents. So we take very long chain alkyl benzene, sulfonated to form aryl benzoic acid, neutralize this with sodium hydroxide, we form the sodium salt, and that's the detergent. Or in some detergent it's potassium salt. Another application of sulfonation is the manufacture of dyes, because the sulfonic acid group impart water solubility. Also, aryl sulfonic acids are important precursors for sulfa drugs. We may get to that later on, sulfonamides. Nitration reaction. To bring up about nitration of benzene, a mixture of nitric and sulfuric acid is used. So the first step will be nitric acid will act as a base, sulfuric acid, much more stronger acid, will act as an acid. So acid-base reaction will form the protonated species. Elimination of water will create nitronium ion, will form the nitronium ion, which will act as electrophile. So the benzene will attack on the nitrogen, forming sigma complex, elimination of hydrogen, recreate the aromaticity, forming nitrobenzene, Aromatic nitro group are easily reduced to amino group using active metal like tin, zinc, iron in dilute acid. So actually nitration followed by reduction is often the best method for adding amino group to an aromatic ring. Nitrobenzene in presence of zinc, tin, or iron in aqueous HCl gives aniline. When benzene is dissolved in deuterated sulfuric, its proton NMR at 7.27 parts per million disappears, and a new compound is formed having molecular weight of 84. What is it? Propose a mechanism of its formation. Sulfuric acid will dissociate to form deuterium ion. Deuterium ion will play as an electrophile. Benzene will attack to form sigma complex. The sigma complex has carbon, deuterium, and carbon hydrogen in the intermediate. Since carbon deuterium is more stronger than carbon hydrogen, in the second step, elimination of the hydrogen will be easier, and deuterated benzene 1D will form. Now, several steps will replace the hydrogens in benzene with deuterium, and the peak in the NMR for the benzene hydrogen at 7.27 will disappear because deuterium will not appear in the NMR, proton NMR region. Okay, deuterium has its special region of resonance. Okay, so in replacing the hydrogen with deuterium, the peak at 7.27 will disappear. And again, the molecular weight of C6D6 is actually 84. See you next lecture.